Welcome to your lesson on dependent events. Let's recap by reminding ourselves what independent events are. So two events A and B are independent if the occurrence of one does not affect the chance that the other occurs. The example we started with was the rolling of dice. As we know, rolling a 6 has a chance of 1 in 6, so probability is 1 in 6. Rolling a double 6, we said all you do is multiply rolling 1 6 and another. So 1 6 times 1 6 gives us 1 out of 36. And again, these are independent because what you roll here on the red die does not affect what you roll on the blue die. So you just, in that case, multiply the two probabilities. So then, taking that same approach forward, when you have 3 dice, the chance of rolling a triple 6 is just the chance of rolling a 6 again, and a 6 again, all multiplied. That only works for independent events. Now today we're going to look at dependent events, and let's see how it changes. So here's the rule again for independent events. Okay, before we do a quick investigation today, let's take a look at some international history in mathematics. In 1933, Russian mathematician Andrei Kolmogorov built up a probability theory from fundamental axioms in a way comparable with Euclid's treatment of geometry. This forms the basis for modern theory of probability. So as you may know, in the Greek times, Euclid was known for building the foundations of geometry in an axiomatic way, which means based on simple facts, he was able to build all kinds of theories in geometry. This mathematician did the same thing with probability. His work is now available in an English translation titled The Foundations of Probability Theory. Alright, so let's do an investigation. So prepare yourself in your notebook. You're going to try some things here and see what you can discover about probability. So we have the situation of having 100 students, 36 of which study art, 40 study biology, and 36 do not study either. Let's begin by filling in this Venn diagram. So here will be art, here will be biology. Okay, so these are the numbers you should have in your Venn diagram. We have the 36 here that do not study either. We have a total of 36 art here, and we have a total of 40 biology here. And as you may remember, the way we got the intersection number is by adding the 36 art and biology to get 76, but we know that that exceeds what we can have in here, which is 64, and that exceeds it by 12. So that's how we get to 12. The question here to start is, if we know that a particular student studies biology, how does this affect the probability they also study art? This is the question we'll build towards as we do this investigation. So number one, please answer answer number 1 and 2 here. Okay, for number 1, we can say the number of students studying biology, which we call NB, is 40. We know that from what's given here, and we know that from the Venn diagram, it's everything in the B circle. For number 2, of those students who study biology, how many also study art? So from the biology group, the number that study art is 12, and we can write that as, let's see. Okay, so those who study art and biology is the intersection area, right? So the art students from the biology students is this section here, which is the intersection, and it is 12. Okay, good start. Let's keep going. This, again, step by step, this investigation will lead us towards something here. So next, try number 3. Okay, so probability a student studies art given that they study biology. And it tells you that the notation for this looks like this. So hopefully you've seen this kind of notation before, but that straight line there means given that, or it's also known as conditional probability. So we're just looking at the same thing we just did in the last problem, where what is the probability a student studies art given that they study biology? So the art students out of the biology students. So we can write that like this, right? So the number of students study art given that they study biology, and we can say that's 12 out of 40. This should not say number here. Let me change this. Okay, that should have said probability because we're looking for probability. So the probability, we know that there was 12 students who study art out of the biology group, but now since we're looking for probability, we say it's those 12 out of the 40 biology students. Thing about the situations where you have given that or conditional probability that the group shrinks from the entire group, which in this case would be 100, to whatever group it specifies, in this case biology, so that the bottom of your fraction here shrinks, it becomes 40. Okay, let's look at the next question. So here, try number 4. This one's tricky, guys. You're trying to now make a rule based on the things you've seen so far. So if you've been doing an investigation on paper, take a look at what you've done and see if you can write a rule that connects these 3 things. So here is that rule, and this is a very important rule in terms of dependent events and probability. So the probability that A occurs given that B has occurred is the number of ways that A and B occur over the number of ways that B occurs. And that's exactly what we just did in the few problems leading up to this, is we had the number of ways that A and B occurs is this 12 here, the intersection. So 12 out of, and then the number of ways that B can occur is 12 out of 40, which represents the number of ways B. So that's the conditional probability that A happens. So A, you can look at this as A out of the B group. So A out of the B group. So here's A out of the B group, 12 out of 40. So that's an important rule, and it's nice to lead up to an investigation through numbers before we go to the abstract, just a formula. Try number 5. So this is exactly like what we just saw, except for now the rule asks you to move from just using the n and n here, the number, to using all probabilities here. And basically it looks exactly the same, except now we have probability here and probability here. This is the rule you'll see in your formula booklet. And the way that works out then is, it seems like the same, right? But basically if we write the probability of A and B, well, the probability of A and B, the intersection, is 12 out of the whole group of 100. And then on the bottom here, the probability of B occurring is 40 out of the whole group 100. But when you write that fraction and you have 2 fractions with the same denominator divided by each other, the 100s can be cancelled, and you just get back to the same thing we have up here. Okay, so now what would the rule look like if you wanted PB given that? So now it's reversing it. So now before it had A given that B, now it's B given that A. So here's the rule we had. What would that look like if you wanted this instead? All right, I hope you were thinking about that and just seeing, okay, maybe I can just reverse the things. But when you write A and B, it doesn't matter whether you write A and B or B and A, it means the same thing. It still means that intersection. So that can be left the same. But in terms of the bottom of the fraction, this says probability of B given that A has occurred. And so as you noticed before here, if this was A given that B has occurred, now we want B given that A has occurred. So the bottom of the fraction is going to be probability of A now, because A is now your full set. That's going to be considered as a full set here. And then that, if you take it and apply, go a little further and use complementary events, so now A given that B complement has occurred, you can just write it like this, right? So the intersection of the two, and then divided by what is your full set now? Well, the full set is, well, given that B complement has occurred, so that is now your bottom of your fractions. So whatever occurs here in the conditional statement is the thing that's going to be the bottom of the fraction. And I hope you see the connection between that and the diagram we've been looking at. Okay, so now rearrange your formula so that this part is your subject. So in this case, we're taking this formula and we're trying to make this part the thing that's isolated on one side. So to get this to be isolated, we just multiply both sides by P of B. So if P of B goes to that side, it is now here. And this is, again, the main formula for our dependent events. As you may remember, for independent events, if we had one thing then another, or one and another. We just multiply the two things. Well, we do the same thing here. If we have A and B, for dependent events, we just multiply the two things, probability of B times the probability of A, given that B has occurred. So here's the main rule there. For dependent events, the product rule looks like this. A and B, we just do probability of A times probability of B given that A. This might look a little different than what we just saw here, but again, it doesn't matter which one's which. It depends on which event has occurred first, basically. So you can see the formula in both forms. And again, this is read as probability of B given that A has occurred. And that can be rearranged as this, and then taking this part and putting it underneath that, dividing by that, so like this. You'll see, I think, both forms in your formula booklet, and they're both used for similar problems, just to solve a different part. Okay, so here's a problem where you apply those formulas. Let's give it a try. You have a sack that has 5 blue, 3 red, 4 black cubes in it, and try question A. Okay, here we go. We're looking for a red, then a blue, so red and blue. In this case, you are selecting a cube and putting it back, and then selecting another. So once you put a cube back, your second selection does not depend on your first selection. So this is still independent events. So even though in this video we're looking at dependent events, this is still independent. So to find probability of getting a red then a blue, you just multiply the two. So basically our independent events formula. And the probability of getting a red is 3 out of 12 and blue is 5 out of 12. So you multiply those and you get 15 out of 144, which reduces to 5 out of 48. Now look at question B. Okay, in B, these are dependent events because when you select a cube, you keep it. So now the contents of the bag change. There's fewer things in it, so the second draw is affected by the first draw. So these are dependent events. The second draw depends on the first. So red then blue. So we have probability of red times probability of blue, given that a red one has been chosen the first time. So here's our dependent events. Notice the formulas are identical, except for now we have this conditional statement here. So chance of getting a red is the same as in the first place, 3 out of 12, but the chance of getting a blue has changed because now there are only 11 cubes left, 5 of which are still blue. So the number of blue is still the same, but the bottom number has changed. So that's a conditional probability. That works out to 5 out of 44. Try C. Okay, C is still dependent, so red then red. So now we have probability of getting a red, 3 out of 12, multiplied by probability of getting a red again, given that the first one was red. So this is dependent again, conditional, and it's 2 reds remain because 1 is gone, out of 11 remain because 1 is gone. So there's our probability. Okay, great. So I hope you see the difference between independent and dependent events. Notice the formula is still the same, still called the product rule, except we have the dependence now. Okay, try to wrap up the investigation like this. So again, the question was, if we know a particular student studies biology, how does this affect the probability they also study art? Well, we had, for dependent events, we came up with this formula. And there's a question here that says, what does this imply about PA and B and PA for independent events? So if this is the formula for dependent events, what does this tell you about this part and P of A if you had independent events? Well, basically what that tells you is that since for independent events this is the formula, that means that PA must be the same as PA given that B has occurred for independent events, because this part here would be like the P of A part in this formula. So therefore this must equal that when we have independent events. Okay, let's try one last problem. So here it is. Please read that. Drawing a Venn diagram might help you, and please answer A and B first. So here's a Venn diagram of coffee and tea drinkers, and here's the answers for A and B. Check your work, see if you agree with those. Basically, those values can be pulled off of the Venn diagram. And now try question C. Here's the answer for C. Check your work there. It's a dependent situation. Now try question D. And here's the answer for D, again, dependent situation.